The limit of today's controllers are, on one hand, the limitations given by the size of the computer on board, which is going to run the algorithms for controlling, and the other limit would be the accuracy of the instruments, which are going to measure the location of the plane, the signals you are interested in, and everything else.
A flight controller is a small circuit board used to control the aircraft. Most flight controllers also use a range of sensors such as barometers and gyroscopes and a GPS to autonomously navigate from one point to another predefined location. In order for an autonomous UAV to navigate, it needs to have a GPS, and GPS signals are very weak and susceptible to jamming or blocking, and any loss of GPS will render the UAV inoperable. We're looking at creating a flight controller which is robust enough to fly without a GPS for extended periods of time, and we're looking into augmenting the GPS signal with other sensors such as LiDARs and cameras to be able to navigate and keep our position estimate accurately enough without GPS. The approach we're using uses an algorithm called SLAM, which is simultaneous localization and mapping, which uses its sensors to create a map in an unknown environment and also at the same time localize itself in the built map in order to navigate. The algorithm has two stages. One is creating the map using the LiDAR, looking at all the obstacles the LiDAR can see. And then the second stage is localizing itself. Using the map it has built, it matches the obstacles it sees to the map and then points where the location is that it believes it is. LiDAR is a spinning laser which rotates 360 degrees and scans the distance between itself and each object in the room or space. Since our research is more focused on the flight controller, we've purchased off-the-shelf airframes such as the DJI S1000 and the 3DR Iris, and we've stripped them of the avionics and installed our flight controller with sensors on it. We have also repurposed old military UAVs and installed our sensors on it.
We are gaining a lot from our collaboration with NASA because they have so much experience in flying planes, and our student can build the controllers. Therefore, we started by building the controllers and all the algorithms only on a computer environment. We moved to the next step of something that we are calling hardware-in-the-loop flight.
In order to test our flight controllers, we first have a simulation environment which we developed, and we have a virtual aircraft, the same dynamics that the aircraft that we're going to fly, and we do different flight modes testing in the simulation. And afterwards we do bench testing where the aircraft is sitting on a bench strapped down so it can't fly anywhere, and we do power on tests and motor on tests, and after we're confident that the aircraft is responding accordingly, we go outside and we have a facility where we test the actual flight of the aircraft. To date, we've done several flight tests outside, and the flight controller has passed all our tests, and we're ready for actual integration of the payloads. And the next steps are to integrate our LiDAR, sensors, and cameras into the flight controller.